we switch from aging disease, from developmental diseases, and we would like to share with you some ongoing studies on post-translational modification of matrix peptides and cellular peptides by phosphorylation. So this is a project of collaboration between UBC in Vancouver, Mary McDougall, and our different groups in Paris. So we will focus on ectopic mineralization and tooth ankylosis in a syndrome called enamel-renal syndrome in two parts. One which will be the natural history of the disease in man and in mice, and afterwards some study on the molecular pathway underlying the disease. So just to begin with, so the tooth and the bone are forming a functional unit, because when you look in the buccal cavity, you have different tissue, epithelial-derived tissue, enamel, dentin, mesenchyme that Claire showed very clearly in her disease, and surrounding cementum and the bone. So the tooth are formed within the bone, and what is important to consider to investigate the disease is that the mineralized tissue are always separated by soft tissue. For instance, the tooth germ have the ameloblast enamel and split from bone with the periodontal mesenchyme and dental epithelial cells. So this boundary, we think, are very important. So we are speaking about the phosphorylation of secreted protein. The FAM20 protein has been discovered some years ago by analogy, by homology, by Nalband, and it was clear that it was in fact the first member, FAM20C, is the bona fide Golgi casein kinase, which took some years to understand that which molecule was doing the job. Secondly, the family is FAM20A, B, and C. FAM20B is working on proteoglycan elongation. And FAM20A, which is the gene important in the enamel-renal syndrome, is very similar to FAM20C, but in fact it's a pseudo-kinase because it had lost during evolution the catalytic important residue, and in fact it is a regulator, a positive regulator of FAM20C kinase activity. That has been very clearly shown by many in vitro data. So what about this FAM20A and FAM20C? Their target is, the kinase target is mediating on a number of matrix protein. First of all, there's protein of enamel, amelogenin, ameloblastine, and amelin, but also numerous proteins involved in bone formation, such as osteopontin or in dentin DSPP. So the motifs are consensus motif, and the FAM20C kinase is acting in the Golgi apparatus, as you can see here, and is important for the phosphorylation of secreted matrix proteins. So what we had the occasion to investigate some years ago, so was access. So we have a rare disease center, and we have 20 families that we are following with this very rare syndrome, because you will see there are not very many cases in the literature. So what we saw is that in fact the enamel was very strange. So they are the first part of dysmorphic enamel, and then we suggested, but it was not availability of the cell observation, that it was in fact an ectopic mineralization and not really per se amelogenesis. So at this time, there are 70 published cases of enamel-renal syndrome, and 36 FAM20A mutations are recorded in the literature. 2 OMIM entries are connected to this so-called enamel-renal syndrome, amelogenesis perfecta with gingival fibromatosis, and enamel-renal syndrome per se. What is important in this syndrome is pathognomonic. When you see the patient, you immediately don't need even to make the molecular diagnosis, because you have an amelogenesis imperfecta, so enamel which is malformed, and also eruption defect. This eruption defect may be moderate, so you will have the partial eruption of permanent teeth, or it may be extremely severe. And in this case, you have only lateral teeth which will be present in the dental arc, and you have to know that in this context, we have to take off all the teeth. That is a terrible surgery, mutilating surgery. Take part of the bone, and you see that the teeth cannot erupt, and it's really the blockage of the eruption process, which is dramatic for the patient. So we manage the patient from early childhood until 18, and then we say, so now you manage very well, and we'll get it off and make implants and denture. So it's a clinical context. So here we have a null mutant, which was published by Vogel in 2012, and I will visit the phenotype with you by electron microscopy. So as you see here, the enamel is quite abnormal when we compare with the control, very regular structure of enamel. And the ameloblasts, you see that the ameloblasts which are making enamel are very long and polarized, and in the context of the null mutant, there is a elongation condition, and there is some figure which make for me, your congress was very informative, because we call that necroptosis, but we have to work with all the parameters you investigate. We have a cell death process in the enamel organ. So, secondarily, we saw some defect in polarization with lateral matrix secretion, and then reverse matrix deposition. So everything is changed, the polarization is altered. And what we saw by labeling is that, in fact, the target of FAM20C and A, the amelogenin, is accumulated inside the ameloblast ghost and also in the enamel matrix. So the consequence is that the enamel, in fact, in issue is not a real enamel. It's made of amylase growth, which mineralized after their necroptosis, and electron matrix dense enamel, pseudo-enamel formation. And what is very strange in situations is you have a direct contact between enamel and the fibroblast. And in fact, in the real life, you are never contact between enamel ameloblast and fibroblast cells. There is always boundaries. The boundaries are during enamel formation, the epithelial dental cells, and later on in adult epithelial gingival cells. So what we saw, that was immediately a reaction, that enamel matrix in contact with the mesenchymal compartment, what it results is an induction of bone formation. You see here the collagen matrix, and you can see that in fact the enamel is bound to collagen-based matrix. And in fact, in dentistry, we always want to make bone. And it's known by therapeutics that amelogenin induce osteoblast differentiation and bone formation. Okay, sorry. So what happens is that in fact this enamel has in contact direct with the muscle make bones, and in fact there is a bonding between the surrounding of the tooth and the enamel. The eruption arrest is programmed, and there is an anchoring of the tooth inside jawbone. So there is an ectopic bone tissue formation bound to enamel, which is completely pathologic. So in fact, what we saw in the mice, you have loss of ameloblast polarity, necroptosis, loss of the epithelial barrier, which is should be there, amelogenin positive enamel, which is known to induce osteoblast differentiation in fibroblast, contact with periodontal mesenchyme, and then you have bone formation which anchor the tooth in the shape. So part of this conclusion is now we want to do a timely removal of this bioactive abnormal tooth germ in order to be able to provoke the eruption. And now Renata will introduce you.
Bonjour à tous, merci Hervé. Ariane a déjà remercié, je me joins à elle. Donc vous avez bien, you heard already that amelogenesis imperfecta is the major phenotype of this enamel-renal syndrome. We tried to understand the other phenotypic characteristics of this syndrome, which include gingival fibromatosis, which is on the left, and also the presence of pulpal stones, which means calcifications within the pulp chamber, in addition to the calcifications within the gingiva. So the pulpal stones are, there is also a bilateral nephrocalcinosis. Actually, we don't have a clue for the pathogenesis of this nephrocalcinosis. And what is interesting is that there is no overt systemic defect in calcium or phosphate metabolism that could explain nephrocalcinosis in these patients. Anyhow, pulpal stones are indicative of odontoblast dysfunction, and odontoblasts are the cells that produce dentin, the less harder tissue of the tooth. And in mice, there was no dentinal phenotype, and we thus wondered whether in man, FAM20A and FAM20C could explain a dysfunction of FAM20A and FAM20C in the dentin, could explain or could contribute to this pulpal stone formation. And I can't go to the, okay. And there on the left, you have a cartoon of a human odontoblast, and the arrow shows the area of where we can see the bulk of FAM20A and FAM20C signal. This signal appears in green on the top for FAM20C, for FAM20A, I'm sorry, and FAM20C here. So both proteins are expressed at the apical pole of human odontoblasts, and they share some co-expression here with the cis-Golgi compartment. In addition, FAM20C has a much wider expression within pulpal cells and endothelial cells. So, theoretically, if, as Ariane told you, FAM20A is necessary to activate FAM20C, we could imagine that the FAM20A dysfunction in the enamel-renal patients could affect FAM20C function also, and maybe affect dentinogenesis. Indeed, in FAM20C patients, dentinogenesis is affected. As you can see here, in this micro-CT image of a deciduous molar of an enamel-renal patient, you can see areas of hypermineralized or hypomineralized dentin, suggesting that indeed dentin is not normally formed in these patients. A most informative area to study in dental tissues is this dentinal enamel junction, which is in the square here, and defects in this region are detrimental to tooth function, since this region is going to avoid expansion of mechanical pressure within the dentin. We used Raman confocal microscopy to do the chemical analysis of this region. First thing is that in normal tissue, you see this nice scalloping, this interdigitation between this enamel and dentin, which allows the dentinal enamel junction to do her function. And this region is almost completely abolished in the mutants. You heard about enamel hypomineralization. We found the same thing using Raman confocal microscopy. This was not a surprise. However, what we found in addition was that this deficient enamel had a very high organic content. On the top of that, dentin had some modifications, a very high organic content also. But as you can see here, the dentinal tubule, so where the odontoblast endings are going to be tracted, this region was abnormally formed compared to the controls. Indeed, you had not only the number of dentinal tubules that was reduced in our mutants, but in some of them, the dentinal tubules were completely disorientated. So we have some subtle dentinal defects in the enamel-renal patients, and clearly indicating that this tissue is also dysfunctioning in this disease. Let's go now further to the gingiva. We did a similar approach. We identified the FAM20A and FAM20C expression in the human gingiva. And as you can see, both proteins are co-expressed in both epithelial and connective tissue cells, and they are also expressed in endothelial cells. So FAM20A and FAM20C have a rather wide expression in the human gingiva. In the patients, the histological image is very similar in all the cases that we have been analyzing up to now, and we can see 4 points. Actually, epithelial and connective tissue defects with abnormal vascularization, accumulation of calcified nodules. These calcified nodules are calcium phosphate, and they can be isolated or creating aggregates. We also found a complete disorganization of collagen fiber bundles, as you can see here, compared to the control, and an abnormally high expression of carboxylated and sulfated proteoglycans. There is another thing that is not shown here, is that inflammation is actually important in the gingiva of these patients. We wanted to understand what was the origin of these defects, so we performed the primary culture of gingival fibroblasts, and we cultivated them in standard medium or in a medium with a mineralization inducing medium. As you can see here, the mutant fibroblasts were prone to mineralize already after 1 week of culture in this specific medium. They were able to create calcified nodules, and the number of nodules was increasing after 3 weeks of culture. The formation of these nodules was preceded and associated with specific markers, including phosphatidylcholine, RANX2, and periostin. What was even more interesting was what Ariane found using electron microscopy, is the presence of these extracellular vesicles, most likely associated with the initiation of this ectopic mineralization defect. Ariane already told you that you have 70 mutations known up to date. These mutations are truncated proteins or mutations within the ATP binding motif, which is a motif associated with this pseudokinase activity, and mutations associated with the FAM20C interactive domain. Our guess was that a mutation within this interacting domain would be deleterious for FAM20A and FAM20C function, and we thought that maybe this mutation was able to lead to a more severe phenotype. Actually, when we analyzed the distribution of these mutants in human fibroblasts, we found that normally FAM20A is expressed in these vesicles. Some of them could be endoplastic reticulum, but we don't have a clear colocalization with that. But anyhow, all the other mutations, including that one which affects the FAM20A, FAM20C interaction domain, was leading to the mislocalization of the mutant FAM20A in the cis-Golgi compartment, as you can see with co-staining with the specific markers. So, whatever was the mutation, the result was the same, at least for the mutants that we have been analyzing up to now, mislocalization of FAM20A within the cis-Golgi compartment. To understand, to find out what was the the mechanism associated, or the molecular pathways associated with this modification. We did mass spectrometry of the conditioned media of the human fibroblasts. And as you can see here, the control secretomes and the mutant secretomes nicely segregate. In addition, on this Volcan plots, you can see that we can clearly separate the upregulated overexpressed proteins from the underexpressed ones. Actually, we identified 69 overexpressed proteins, 40 underexpressed, but we focused only on the classically secreted ones, which diminished the number to 12 and 25. Among the 12 underregulated, underexpressed proteins, we identified a very strong interactome between these proteins. I'm not going to give any details, but this interactome was clearly associated with a decreased capacity of the FAM28 deficient cells to degrade the extracellular matrix. The overrepresented proteins were forming another network. Almost all of them who were able to make a network around TGF-beta2. You all know TGF-beta2, a main protein in the fibrotic process. So in our patients, what we found was that both extracellular matrix degradation was decreased, and the capacity of the connective tissue to make fibrotic to be overproduced was increased, and this was associated with increased TGF-beta levels, mainly TGF-beta2. And in agreement with that, the signaling pathway, so the expression of the classical TGF-beta pathway effector phospho-SMAD3 was increased in all the patients, and that we found on Western blot, and also when we looked within the cells, you can see that natural cells cultivated under standard conditions had already phospho-SMAD3 staining within the nucleus. When we added TGF-beta1, these cells were able to answer even more, suggesting that this TGF-beta pathway could be self-sustained in our mutants, in our patients. When we looked in the gingiva, in order to identify whether the TGF-beta pathway targets were also upregulated in vivo, we indeed found that phospho-SMAD3 was localized in the nuclei of the gingival fibroblast. Here we are in the connective tissue, but also other targets like neutrin-1 involved in inflammatory healing or collagen cis-A were also upregulated, and here you have also some disorganization. And I'm going to stop here just by summarizing our observations. Dramatic enamel hypoplasia, some subtle dentinal defects, and calcification and fibromatosis that could be explained by an impaired TGF-beta signaling when FAM28 is dysfunctional. And thank you very much for your attention.
Thank you, Ariane. Thank you, Renata. So is there any question in the room or in the chat? We have time for one, maybe two. No? No question? Yes, again.
Thank you very much for the combined presentation, very nice. I have a question about TGF-beta. Is it, what about the other classes of TGF-beta? You have looked, you have evidence TGF-beta1. What about 2 and 3, the others? Are they not relevant?
Actually, yeah, thank you for the question. Actually, TGF-beta2 is the most The most upregulated, we have an increase of about sixfold of TGF-beta2, and then TGF-beta1 is increased by about 3 times. TGF-beta3, we didn't see any different modifications, but TGF-beta2 and TGF-beta1 were the most expressed.
Okay, thank you very much. Yeah, there are always discrepancies between, we see that also in osteoarthritis. Thank you, Renata.
Okay, great.
Yes, I had a question for Ariane. Good work, congratulations. And just one question, you said that you believe that ameloblasts died by necroptosis.
Yes.
And why you think this type of cell death
So
occurs?
we exclude apoptosis due to the electron microscopic structure of the cells. So of course it's a superficial analysis. We have to map more precisely. But we didn't have the fragmentation. The apoptotic figures were not present. And it was the membrane are completely destroyed. But as I saw all your presentation, I want to do with the nuclear protein. I want to do what you do with extracellular mineralization. I think that it's a nidus for the mineral.
But that's a reason to privilege necroptosis as
Yes,
compared to
it's
necrosis?
ultra structural aspect. Yes, but of course we could do a whole study exclusively on this cell death process.